Good afternoon to everyone, and welcome to the first this year colloquium, Jerzy Pniewski and Leopold Infeld colloquium. And since this is the beginning of the year, let me wish you all the best in the coming year, successes, and many interesting talks to listen to during the next departmental colloquia. And today we have a pleasure to have Professor Rafał Demkowicz Dobrzański, the expert on quantum technologies and quantum metrics, or quantum metrology. And today he will talk about quantum technologies, Anno Domini 2020, expectations and reality. So, please.
Thank you very much. So it's a great pleasure to be here. And I hope this talk you will find enjoyable. So let me start with some visions from the past. So this is quotation by Richard Feynman from one of his public lectures. There is plenty of room at the bottom. Nothing that I can see in the physical laws says that computer elements cannot be made enormously smaller than they are now. And another quotation. Now we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. The ones move around, the zeros move around. Finally, along a particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant. So this shows that Richard Feynman is, for people working in quantum technology, kind of founding father, a visionary to whom we like to refer. And now, after this couple of years, we have more visions and money coming with it. So I will tell you about few initiatives that appeared recently. One of them is European Union Quantum Flagship Program, launched in 2018, which is a successor of two other EU-founded scientific programs, Graphene Project and Human Brain Project. So this is like a third big scientific initiative for which it's 1 billion euros is dedicated over next 10 years.
European or American billion?
European. No, billion, I mean milliard. Okay. So billion, I think both in American English and British English it's billion, no? Oh, sorry. Yeah. Then I'm. Okay. But it's also B, written as B. Okay. So if you read the so-called Quantum Manifesto, which was a manifesto preceding the starting of this program, you can find such a long-term goals. So long-term means longer than 10 years, probably. So quantum internet connecting major cities in Europe, a universal quantum computer, and on-chip quantum sensor devices that can integrate within mobile phones. So I do not mention short-term goals, which are a bit more realistic, but I just mentioned these most ambitious ones, which are long-term goals. So European Union is not the only one that's in play. Actually, okay, UK program was before that, so still UK was in EU. So it preceded a bit this initiative. It was preceded by a UK initiative. Then you have the US initiative as well. So if somebody thinks Donald Trump only launches missiles, then he also signs things like this. So there was Quantum Initiative Act, which is a money supporting companies that work in quantum technologies. It's also comparable amount. And there is also Chinese founding, which is a bit 10 times larger. And and it's dedicated for establishing like a center for quantum information sciences. This year it should be completed in Hefei, I think. Russia also has a quantum institute in Moscow, or which I have not mentioned here, but also Russia is investing a bit. I don't know exactly the amount of money, but as well. So Japan as well. Okay, I did not mention everybody, but. And also there are commercial companies that invest money in this technology, or they invest money that they take from the state to develop quantum technologies through things like this. But they are really, I mean, the well-known names. So to allow you to maybe move around this field of quantum technologies, I would divide it into three pillars. So if you want to somehow in a systematic way think about quantum technologies, you can divide it into quantum computing, quantum communication, quantum metrology subfields. Okay, so me personally, I'm working in this field. So I feel most comfortable within this pillar. But today, I don't want to make a overview of everything, because it's not possible, and also then probably you would not be able to distinguish between real things and some marketing things and some PR, which is just promising that they did something and they did not really deliver this, or they just cheat in some way. So I decided just to focus on three particular achievements which have been achieved in the last year or 2 years. One from the quantum computing field, one from quantum communication field, and one from quantum metrology field. And I hope that thanks to this, you will be able to put these visions that I described before into a real context, what has been achieved and where we are at the moment. Okay? So let us start with quantum computing. So just a basic introduction, what is quantum computing? So we think about a qubit, which is a generalization of a bit. So we can have superpositions of zeros and ones, for example, a two-level atom or some other two-level quantum system. And what is the essential feature that allows us, in principle, to compute something faster than using classical device? The buzzword here is quantum parallelism, okay, which simply means that if we have some logical circuit, this is like quantum logical circuit, but you can think also about it a bit in terms like classical logical circuits that compute some mathematical, does some mathematical computation, which we represent by a unitary matrix, because in quantum mechanics evolution is unitary. And then we send some input state through this unitary, and then we get some output state, and this is computation. And now, what is quantum parallelism? Quantum parallelism is simply reflects the fact that thanks to the superposition rule, we can send into this circuit, which computes something, a superposition of all our qubits, a state which is a superposition of all possible binary inputs, okay, to this computation device. So if we have like n qubits, we can encode 2 to n numbers, so we can prepare our input state in a superposition of 2 to n states representing 2 to n different inputs, different data that we send. What? Yes, but did I say something wrong up to this point? No. I just said that you can prepare such a state. Now, you send it through this quantum channel evolution, and then this U acts on each of these terms and prepare the superposition of this output states. And in each of these output states, you can say that there is, in principle, encoded a solution to this computation for a given input data. It's encoded, but it doesn't mean we can read it out. I agree. So that's the trick with quantum algorithms. Now, you should think about a clever way how to benefit from the fact that there are these solutions there, but if you perform just a measurement in the standard basis, like just measure in the end zeros and ones, it means you would obtain in the end a result corresponding to one input data. Okay? And in this way, you do the same as classical. So one run is one computation, and moreover, you did not control which input data you computed this result for. So it's not very useful, but you may try to engineer an algorithm where you can benefit from this. And if you can benefit from this, then in principle you can have exponential speedup. Okay? Because you have 2 to n inputs computed in one run. Okay? So the first algorithm, and also the one that illustrates this idea in the best way, even though this algorithm is not useful from a practical point of view, but it illustrates the idea. And if you understand this, you understand the idea. So the Deutsch algorithm, in the simplest formulation, is the algorithm where you have a function which as an input has 1 bit and as an output has 1 bit. This is a classical formulation first. And then your goal is to decide whether this function is constant, so it returns the same value for both inputs, or it returns different values for different inputs. Okay? And that's the goal. And if this function is just a classical, if it's encoded in a classical device that you can press the button and calculate it, you need to run it twice for 2 input data, okay? For 0 and 1, to answer this question. So you require 2 runs. Now, if you have a quantum box that computes this function in a way that it gives you a minus sign in front of a qubit state x if function is 1 and gives you plus sign if value of the function is 0, then you can run this operation on a superposition of zeros and ones, okay? And then you will obtain the following superposition. And now, if the function is the same for 0 and 1, it means that you either this function is 0 or it's 1, the value of the function. So either you have 0 plus 1 or minus 0 minus 1. Okay? And that means that if you think about a vector in a Hilbert space, you have this vector 0 plus 1, or with a minus sign, which is just a global phase, so it's not a physical difference. On the other hand, if you have function which has different values, you will have effectively a state which is 0 minus 1, which is an orthogonal state. Okay? And now, because these are orthogonal states, you can distinguish them. Okay? So in the end, you measure whether you have this state, and you know which of these 2 cases you are in. So even though you did not learn what is the actual value of the function, you know that it's the same for 0 and 1, or is different for 0 and 1. Okay? And that's the essence of quantum algorithms. Just make some clever, first invent a problem where this is useful, and then make this algorithm work in a way that, in principle, it requires computation of all values of the function, but in the end, you are not interested in particular values, but some relation between them that you can learn about by performing, for example, a single measurement in the end. Okay? So that's the essence of quantum algorithms. And if you are a computer scientist, so you are a person working on the other side of the street, you usually plot this kind of eggs, which describe different problems as belonging to different computational complexity classes. So, for example, P are algorithms that run in polynomial time in terms of number of digits of the number you want to do something, while famous NP computational class is the class of algorithms where you can check the answer in a polynomial time, but it doesn't mean that you can obtain the answer in a polynomial time. You can just check whether it's a correct answer in polynomial time. And then there is this famous question whether P equals NP. So actually, as you see, nothing is known in this field. It's just that you plot these different eggs, and you assume that, for example, something is not true, and then from this you draw some conclusions in this theory. So now, if you have this X, what quantum computers change in this picture? So where is this egg corresponding to quantum computers? It's probably somewhere here. So it means that in principle, maybe if there are some problems which are not P, so not polynomial, maybe they can be solved in polynomial time by quantum computer. Okay? What?
This thing we are talking about is how to use quantum computers to solve NP problems fail.
But we, come on.
Because short algorithm cannot help you. Because it's not that NP is complete.
Ah, you added now complete. Okay? I'm not talking about NP complete at all. Okay, so I'm just talking about NP. So it's not, again, it's not relevant. So short factoring is probably NP, which is not P, probably. But so okay. Now, so first of all, first message. Whatever quantum computer can do, classical computer also can do, but maybe in exponential time or exponential memory. Okay? So this is one message that I want everybody to understand. So quantum computing is just multiplying vectors by matrices. Okay? So we can always simulate it on a classical computer, but the size of matrices grow exponential. So for example, if somebody thinks about like undecidable problems like related with Gödel theorem, so quantum computing has nothing to do with this. Okay? So if something is undecidable for classical computer, it's also for quantum computer. So we just fight for some exponential speed up for some problems. And actually, there are a number of algorithms that appeared. And if you are interested, you can go to this webpage, Quantum Algorithm Zoo, where I guess you have like maybe even 100 algorithms, which is a lot. But of course, most of them are just variations over some few conceptual different classes of algorithms. So it's not so nice that we have many different type of algorithms. We have few classes of algorithms and some variations over this. But the field is developing because some progress has also been made in 2016, where there was this algorithm that supposedly get exponential speed up for so-called customer recommendation systems, which are the systems which tell you what movie you should watch next if you watched a few movies before, like on Netflix or somewhere like this. But unfortunately, 2 years later, a classical algorithm was developed based on these ideas that show that it also can do it with the same scaling. But anyway, I mean, thanks to this algorithm, classical algorithm was developed. So it's really in field that it's developing, and it's not obvious that we will not have some new algorithm next year. So, okay, how to build quantum computer? You have different physical platforms that people are trying to build quantum computer on. So you have ions, you have photons, you have many others, but recently the biggest progress was in the so-called superconducting qubits. So qubits which are built on superconducting elements, where basically the qubit is a superposition between states with different number of Cooper pairs on some superconducting piece. Okay, that's maybe enough to call it like to say about it. And in 2017, IBM was proud to have this 50-qubit quantum computing device. You have a commercial company called D-Wave, which is breaking records with number of qubits they have, but they don't care about the quality of their qubits. And moreover, they follow a different computational paradigm. They do not use this gate paradigm where we combine our circuit from gates, but they use something which is called adiabatic computing, which is just utilizing the adiabatic theorem from quantum mechanics, that you would have Hamiltonian and you then tune it very slowly, and in the end you expect that your final state is the ground state of the Hamiltonian, which is also the solution to your mathematical problem. So they just play such things, but they have no guarantee that they have some speed ups at all, because their system is too noisy. So I just mentioned this to tell you that this is a different approach and also not really well. Okay, it's not really quantum computer. It's quantum annealing device. Okay, you can call it, or quantum inspired annealing device, which is too noisy to really manifest strong quantum effects. Okay, but last year, probably many of you have heard about the Google, who announced the 53-qubit quantum device, where they claimed the so-called quantum supremacy demonstration. So here is the text from this. Here we report the use of a processor with programmable superconducting qubits to create quantum state on 53 qubits, corresponding to a computational state space of dimension 2 to 53. Measurements from repeated experiments sample the resulting probability distribution, which we verify using classical simulations. Our Sycamore processor takes about 200 seconds to sample one instant of a quantum circuit 1,000,000 times. Our benchmark currently indicates that the equivalent task for a state-of-the-art classical supercomputer would take approximately 10,000 years. So actually, what does this computing device do? It simply runs some random computation, which means that if you have some random quantum circuit, so you have some quantum gates, and you choose them randomly, okay, on these 53 qubits, and in the end, you obtain some probability distribution for your measurements. So now they just run it, and then they sample from this probability distribution in the end, and now they say that if somebody wanted to use classical computer to simulate this probability distribution, like knowing the set of gates that they used, they would not be able to do it, or they would need 2,000 years or something like this to do it. So to reproduce the distribution of results that they get in the end. Okay? So it's not a very interesting computation because it's just a random quantum circuit. So as I said, the goal is to sample some probability distribution that results from this quantum circuit. And they claimed in this paper that they achieved this level that no classical computer can simulate it in a reasonable time. And then a few days later, IBM claimed, we argue that an ideal simulation of the same task can be performed on a classical system in 2.5 days and with far greater fidelity. And the reason was that IBM has a supercomputer with a huge memory. So actually they have 250 petabytes memory. And actually you can store this quantum state faithfully there. So this 2 to 53. While Google, when they were claiming this 2,000 years, they based this computation on an algorithm that doesn't require storing the whole state simultaneously, but just splitting it into some parts to reduce the memory demands. So actually, this was a rebuttal of this claim. But, I mean, to be honest, it's still an achievement because you can imagine that now Google, I guess, in 1 year, they will increase this number of qubits by 4 or 5. And then this memory will be quickly, consumed. So people in quantum computing field call the era we are in like noisy intermediate scale quantum computing. So what does it mean? It means that we have noisy elements, like errors in our gates are still of the order of 10 to minus 2 or 10 to minus 3, which means that if I perform some quantum gate, I have like 1% or a bit less probability that it just generates some random state. Okay. And that's too much, in particular to implement the so-called quantum error correcting codes. So that's why people try at this moment just to find any kind of task that the quantum device can beat classical devices. Okay? And this is called this quantum supremacy challenge. Okay? So to find anything, not useful, not interesting, but anything. Because actually, if you look deeper into what Google is doing, they also have these noisy elements in their system, which means that if this is this probability distribution they sample from, want to sample from, what they actually sample from is a mixture of this probability distribution with 2,000th weight and a random, just flat probability distribution with 0.998. It's because of noise. So they just have a small signal, I mean small, like this, on this noise floor. But it's still okay. It's still enough. If you sample many times, you can have a significant signal from this. So now, this is the present, this is the moment we are in. And now, if we want to go further, this level of errors needs to be reduced to approximately 10 to minus 4. So it's like order of magnitude and a half still to go, if there is to be some spectacular breakthrough. So it's not unimaginable, because already these levels were very ambitious like 10 or 20 years ago. They started from like errors on the level of 1% or even more. So they've made already an order of magnitude or more improvement. So now I would say that we are in halfway, till the moment that our elements are that good that we can implement so-called quantum error correcting codes, which essentially do things like this, that you increase the number of elements, but thanks to the fact that these elements are good enough, as a whole, it has effective lower error than the components. Okay? And then you can build and scale up these things. Okay, so this was quantum computing, this achievement. Now, quantum communication. I will just focus on quantum cryptography. So maybe you know that you only believe in these things because you know that factoring is hard, or you believe that factoring large numbers is hard. Because what effectively we are all using is the so-called RSA protocol that utilizes a public key. So if you want to transmit your credit card number to a shop that you want to pay for something, then the shop generates the so-called private key, so 2 numbers, multiplies it, and announces the result as a public key. Then you use this public key to encode your credit card number, but in order to decode it, you need to know what numbers were multiplied. To encode, you don't need it. To decode, you need it. Okay? And now, if we use like 4,000 bits numbers, no classical computer can do it. But as we know from quantum computing stuff, there is a quantum algorithm, Shor algorithm, that indeed does it. So now all these things will be insecure if we had quantum computers. So how to have secure communication? So there is some way of encrypting messages which is 100% secure, and probably 100% secure. It's called one-time pad. It means that if 2 parties share a random key which is equal to the length of the message, and it's private, so it's not known to anybody else. So then if these 2 parties have this secret key that nobody knows about, and they want to transform a message which is the same length as this key, and if this key is indeed random and secure, so it's the same but random to everybody else, okay? Then they do just simple addition modulo 2 of every bit, and because the key is completely random, it means that it randomly flips or doesn't flip a bit, and in the end you obtain a completely random sequence of zeros and one. Completely random from the point of view of somebody who doesn't know the key, okay? And it's probably completely random, so you cannot decode it in any way. Then you send it, and the receiver does the same. So again, adds modulo 2 the same things, but because adding modulo 2 twice returns to the original sequence, you have the information recovered. Okay? So the only problem with this method is that you need the key that is equal to the length of the which length is equal to the length of the message. So you need to distribute it beforehand, okay, in a secret way. So the challenge is how to distribute the key, especially if we don't want to meet with each other under the bridge or somewhere to distribute this key. But we just use some internet connection and want to send our credit card number or something. And that's where so-called quantum key distribution enters. So quantum cryptography should rather be phrased quantum key distribution, but because it's not about cryptography, it's about secret key distribution. Okay? So which then we can utilize to some classical cryptographic methods like this one. So the original protocol, the first protocol that was proposed by Bennett and Brassard in 1984, and it's very simple, and it's best to understand it using the qubit, which is encoded in polarization state of a photon. So you can imagine that if you have a plane wave, and you have a plane wave with vertical polarization, you associate a photon with it, which we'll say has vertical polarization, and so on with horizontal polarization state. And then arbitrarily linear polarization will be this, so polarization that is in alpha to the horizontal plane, is inclined with alpha angle to horizontal plane, will be given as such superposition. So this is actually a qubit. You can have also complex amplitudes, then you will have elliptical polarization, but we don't care about it. And then what is the measurement? The measurement is just putting a polarizer for this photon. And if you put a polarizer that transmits vertical polarization and kills horizontal, you effectively perform a measurement in this orthogonal basis. Yes? So in this 0, 1 basis, if you put it like this. Mogą być. So bardzo różne, there are different kind of photons. Sorry, I switched to Polish, I don't know why. So there are different polarization states of photons, and there are as many polarization states of photons as, at least as in classical optics, and even more. Okay. Okay, so then how to use this qubit encoded in polarization states to distribute secret key? So how this protocol works. So imagine we have a quantum channel, for example, optical fiber, and we also have a classical channel. And both of these channels are not trusted, so they can be eavesdropped. And now the protocol goes like this. So the sender sends one of 4 polarization states. He can or she can say polarization state horizontal, vertical, or 45 degrees or 135 degrees, randomly chooses one of these states. And the protocol makes the following assumptions: that states 0 and 45 are understood to carry logical bit 0, and states 90 and 135, they carry logical value 1. And effectively, you can see that we are using 2 different orthogonal bases. Okay? These 4 states, they correspond to 2 different orthogonal bases. And now what does receiver do? The receiver randomly chooses one measurement basis, either vertical, horizontal, or 45, 135 degrees. It's random. Okay? So then what happens? If the sender sends one of these states and the receiver measures in this basis, the receiver learns perfectly what was the value of the bit. So if sender sends it 0, the receiver will measure 0, and this will be logical value 0, and so on. But if bases are misaligned, so if the sender actually sends 45 degrees and receiver measures in this basis, then there is a random result. So with probability 1/2, the receiver will say, okay, I got logical bit 0, or I got logical bit 1. So there is like just noise. So what do they do in the end? After the transmission is complete, they call to each other just by classical channel, and the receiver tells the sender which basis he or she used in a particular run, time slot. Okay? And then the sender tells the receiver, okay, this time you were aligned, this time you were misaligned. And they throw away the bits when they were misaligned. And they keep only the bits that were when they were aligned. And in this way, they have ideally the same sequence of zeros and ones, while because the eavesdropper could eavesdrop only before they informed each other about which basis the receiver chose, the eavesdropper, when he wanted to learn about the state, would need to distinguish between these 4 states, okay, without knowing from which basis they come, because this information came later, what was the measurement basis. Okay, so you would need to distinguish between these states. And these states, for example, 0 and 45, they are not orthogonal. And fundamentally, you can prove that you cannot distinguish perfectly non-orthogonal quantum states.
If the transmission may be eavesdropped, why there may be not 2 eavesdroppers, one which is eavesdropping in basis 1 and second in basis 2?
Because you have a single photon, and you have to decide which basis you measure in. Because once you measure, the second measurement tells you nothing, okay? Because you project the state on one of measurement basis states.
But that makes any type of eavesdrop void, basically.
I mean, I don't understand.
I mean that if I try to eavesdrop such photon,
Yes.
measure it, then it wouldn't take to the receiver.
So, okay, so of course, if somebody cut the fiber and takes all the photons, then the receiver will see, okay, my fiber was cut, okay, let's use another fiber. Okay? But if the eavesdropper is more clever, he will eavesdrop and then resend some other photon to mimic the original one. So he will resend the photon that he thinks there was, okay? But because he cannot learn it perfectly, he will introduce disturbance, like noise, because, okay, maybe sometimes he's lucky and he will send the correct state. But you can calculate it quantitatively how often he will introduce errors, okay? So there is like a fundamental trade-off. The more information the eavesdropper wants to learn about states which are non-orthogonal, the more disturbance he introduces, okay? Yes, of course. This is closely related to no-cloning theorem, which is actually closely related to the fact that non-orthogonal states cannot be distinguished. Because if you could clone non-orthogonal states, then you would make many copies, and then you would measure them, and you would learn perfectly. Because if you have many copies of some state, you can learn it perfectly. Okay? So this is closely related to cloning as well. So this is the essence of the security here, that, okay, I didn't say everything. So of course, they might be an eavesdropper, so then you need to check afterwards whether the eavesdropper was eavesdropping. So you need, in the end, to sacrifice some of these bits that should be correct to sample from them and check whether they are, acceptable level of errors there. Because if errors are too high, you can infer that eavesdropper could have obtained, for example, more information than legitimate user and so on. But if errors are relatively low, like below 11%, you can make the protocol completely secure in the end, and this still so-called secure key. Okay. So now, what is the main challenge in implementing this protocol? The main challenge is photon loss, because you use single photon. Okay. And then you want to send it, for example, through the optical fiber. This is the easiest way to do, in principle, because the optical fibers are everywhere. But even the best optical fibers, if you choose the best ones and choose the wavelength so that the losses are as low as possible, so this corresponds to infrared radiation, 1,500 nanometers, the loss is 0.2 dB per kilometer. What does it mean? It means that probability that a single photon sent through a 400 kilometer transmission is 10 to minus 8. Okay, so that means that it's very low probability that your photon survives. But is it the end of the story? So maybe not, because maybe, okay, it's enough for you. Actually, if you have like a gigahertz repetition rate of producing your photons, you can obtain a few bits per second key generation on the length of 400 kilometers optical fiber. And if you can prove that it's really secure key, maybe 6 bits per second is not so bad to generate really secure key on such a distance. So this is more or less the present day record in terms of optical fiber quantum key distribution, okay, 400 kilometers. But you can change the setup a bit and don't use optical fibers, but just send photons through through free space. Okay? And of course, it's maybe not very practical to just send it through the free space in the atmosphere, but it's a good idea to use a satellite. Why? Because of course, in atmosphere, you also have losses. But actually, the atmosphere is very thin. It's just approximately 10 kilometers. Okay? So even if you have losses the same as an optical fibers or even larger, you need just to go out of atmosphere to satellite, and then if you are out of atmosphere, there are no losses anymore. Okay? And then come back from the satellite, it's another 10 kilometers. So actually, if you calculate it, it's effectively in total 5 dB loss if you go through the 10 kilometer width of, through the atmosphere. Okay? So 5 dB is what you would get here for 20 kilometers or 30 kilometers fiber. Okay? And now, of course, you have other issues like your beam is diverging. So you will lose a bit because for example, your telescope will not gather all the light. So you have additional losses from there. But actually, it will be like maybe additional. It does. Its wave function diverges, so it can be observed in places where you don't want it to be observed. Okay, you would like to collect it on your telescope, while the probability distribution is larger than your actual telescope. So there are difficulties, but there are results which are quite promising. So this was this Chinese satellite 2 years ago, or 2.5 years ago, that was the first quantum satellite, where they showed that the communication from satellite to ground station, that is 1,200 kilometers long, and they were able, over this distance, to distribute secure key at a rate 1 kilobit per second. Okay. Yeah. So you can. Okay. So there were other records that if you establish secure key with one ground station, and then establish secure key with another ground station, then effectively you establish secure key between 2 ground stations, provided you trust the satellite. Okay. So that's the record for providing you trust the satellite. So now you have other quantum cryptography protocols that are based on entangled states. In fact, they are very similar, apart from the fact that you don't use one photon, but you use 2 entangled photons. And now both parties measure the photon, and they also obtain some correlated results. And actually, this protocol was invented by Arthur Eckert in 1991. And effectively, the security, this protocol is probably not the technologically simplest choice, but it's appealing from a fundamental perspective, because here you can somehow relate the security of this protocol with the fact that there are no local hidden variable models that lead to violation of Bell inequalities. So that quantum correlations are so strong that they cannot be mimicked by local hidden variable models. So in a sense, before the measurement of these actual bits, these bits are not existent. So nobody could just know them and send to the parties. They just generate them at the moment of the measurements. Okay, so and the security proofs are related with so-called quantum correlations, so correlations that violate Bell inequalities. And again, the same satellite has this record of distributing entangled two entangled photons to 2 ground stations, which are distanced by 1,000. The distance between them is 1,200 kilometers. Okay. Okay. So 5 minutes. Yes, maybe. So I have 5 minutes for this last part for quantum metrology. So let me just be very brief. So the goal of quantum metrology is to manipulate individual quantum systems in order to enhance the measurement precision, utilizing quantum coherence or ideally quantum entanglement as well. Okay? So I will just focus here on optical interferometry. Okay, so optical interferometry, in a sense, classical interferometry is also quantum, because we use coherence of light, which on the level of photons is coherence of photons. So the photon is in a superposition of traveling two arms, in fact. So we actually use coherence in standard optical interferometry from the point of view of photons. But now you can try to think what more you can do if you want to utilize non-classical states of light, so the states of light in which photons are entangled. Okay? So there are some quantum correlation between photons, and so I will skip these two other fields, just let me focus on this classical interferometry example. So if you have a Mach-Zehnder interferometer and want to estimate the phase, and you send like a coherent state of light, in the end, your detectors will detect some number of photons. This is your measurement. And on average, this number of photons, they depend on this phase just via standard classical computation of your output intensities of your wave. Okay? So they are just fringes. Yes? So depending on the phase phi, we have sinusoidal dependence of our intensities in the end, so the average number of photons. But now you obtain a particular number of photons, and you have to infer the phase from this. And actually, you can prove that the best estimator you can find is an estimator that simply inverts these formulas and calculates phi as a function of Arcus cosine of the difference of number of photons. But in every run, you will obtain a bit different photon numbers because of Poissonian statistics. Okay, you obtain. So you will have some spread in your estimator. And actually, this spread will be proportional to 1 over square root of the number of photons that you use in your beam. And this is called so-called shot noise scaling. So it means that if you want to estimate the length difference of two arms of the interferometer, basically it's wavelength, but over square root of number of photons that you use for interferometry. Okay? So now you can use non-classical states of light. And the first proposal was already put in 1981 by Carl Caves, where he proposed to send additionally to the other usually unused input port the so-called squeezed vacuum state. And squeezed vacuum state is a state which has average values of electric and magnetic field 0, so that's why it's called vacuum. But additionally, it has fluctuations which are squeezed compared to the vacuum state. So you can say that electric field fluctuations are smaller than in vacuum field, but magnetic field fluctuations are larger than in the standard vacuum state. Okay? And if you do it in a clever way, so basically you choose the orientation of this ellipsoid properly, so you squeeze proper field, proper so-called quadrature of the field, then in the end you can obtain a sub-Poissonian statistics of this difference of these photon numbers. So there is no shot noise anymore, there is something which is sub-shot noise. There's less fluctuations in this photon number difference. I mean, I'm not explaining it so you can believe it as it's calculated, I'm just stating the result without a proof. So if you don't understand why is it so, then it's perfectly fine. I mean, but intuitively, it's that we reduce fluctuations in some appropriate quadrature, which translated then to reduced fluctuations in photon number difference. And that's why you can obtain an improvement in estimation precision. And even though I'm talking here about squeezing vacuum, depending on the picture you use, you can also understand it as a way in which photons are entangled with each other. Okay? So in some sense, this squeezing can be translated to entanglement between photons, if you look at these states from a photon perspective and not from the mode perspective. And then you can show that in principle, if you squeeze very strongly, you can obtain scaling which is quadratically better. So it's not lambda over square root of n, but lambda over n, over number of photons. Okay. So this again, ideal thing. In practice, we just fight to see some improvement. Okay. But actually, the good news is that this actual protocol has been demonstrated useful in gravitational wave detectors. And the real proof was, the real implementation has been just completed last year. So before that, these were like proof of principle experiments showing that it should work. And just last year, the real squeeze light source was implemented both in LIGO in US, in these two detectors in US, as well as in Italian detector Virgo. And this idea is, as I told you, just send squeezed light into the unused port of this interferometer. In this case, it's Michelson interferometer. Michelson interferometer. But it's the same as Mach-Zehnder interferometer in a way. You just have inputs in the same place as outputs, but apart from this, everything is isomorphic.
Let me interrupt you and say one thing. That 20 years ago, Professor Demkowicz gave a very similar talk when he proposed to use a squeezed photon state to the measurement of gravitational waves.
Yes.
That time it was just a proposition.
Yeah, because he worked with caves. Professor Demkowicz collaborated with caves.
I don't know.
Yes.
I don't remember now.
Yes.
But he was a chief of a cathedral.
Yes.
Okay.
Yeah. So it's really something to be remembered that last year this was finally done. The improvement, as you can imagine, maybe it's not spectacular, but it's like 35% reduction of noise thanks to squeezing. So if you compare this green curve with this black curve, this is what you gain in terms of reduction in noise in gravitational wave detectors. So what does it mean? That you can detect gravitational wave which has like 35% smaller amplitude, okay? Which is not so bad, taking into account that to obtain the same thing in other way, so just by cranking up the power of the laser, you would need to increase the power of the laser by 85%. So almost twice, which already, I mean, this laser is operating already at its limits, and increasing its power more would introduce many instabilities in the system and so on. And now the question is, how many photons do we actually send here, okay, in this other input port? And the amazing thing is actually that we send like almost nothing. It's like this squeezed vacuum state. Of course, it has photons because it's not vacuum. But if you compare it, what you would have to do here, so you would need to increase the power by like 12 watts, which means more or less 10 to 20 photons per second more being sent into the gravitational wave detector. While here, with this squeezing, you basically send like 100 photons per second additionally. So like nothing. So this nothing gives you an observable improvement here. So this is really amazing that because these photons are in special non-classical state, they do the thing that classical photons would need. I mean, you need 10 to 20 classical photons to do the same. Okay, so, okay. You can also expect that the event rate, thanks to this, will be increased by 50% of detected number of binary neutron star merger. Okay, so that's the end. So just I will end up with this slide. So if you want to understand where we are at the moment, just please remember these three examples. Yes, like this Google processor, which almost does this quantum supremacy demonstration, this quantum satellite, and the gravitational wave detectors that utilize now squeezed states of light. But of course, we have challenges here, which we have to maybe overcome. Thank you.
Thank you very much for this very nice talk. You already asked some questions, so maybe you can wait, Marek, later.
Could you maybe say what are the challenges? And like very briefly, is it mainly technological, do you think, or there are some theoretical also challenges here? In order
Theoretical challenges.
Well, I don't know. I mean, the thing is that for sure for these devices to work, there must be a device that's built, right? So.
Yeah, I mean, I don't know of any like fundamental challenges apart from this. I mean, technical challenges that we need to reduce noise to reach, for example, in quantum computing, reach this level where we can use this error correction. While, for example, in quantum communication, to enhance the distance of communication, we should, in principle, develop the so-called quantum repeaters, which are some way to overcome the no-cloning theorem by using entanglement teleportation using entangled states and reducing the effective loss on a channel which is very long. While in quantum metrology, these advantages we have in LIGO, they would be much more if we just reduce loss a bit. Okay, so the loss is the crucial thing in these interferometers, for example.
To the quantum communication part, when you describe the possible eavesdropper, you assume that the only form of noise is in the form of absorption of photons. I guess there are also some other which rotate the polarization.
So just to put it quickly, I just said it like this to be simple, but the proofs are for the most general quantum attack you can imagine with quantum memory that you keep with yourself until you learn what they communicate with each other to tell what basis they measured in, and then you only measure things that you kept on. So it's fully general consideration, like arbitrary quantum attacks.
Even including, for example, that the eavesdropper is there from the very beginning and is mimicking is pretending that the fiber is more noisy than it is.
Yes, it could be like this. The only assumption is, in the end, when they communicate with each other through classical channel, they should know that they talk to each other. Because of course, if you completely mimic the sender and you also communicate by classical channel with the receiver, then there is no way. But so there is something that you require, which is called authorization, okay, or authentication, okay, something like this. So this you require from the beginning, but this is like a fundamental requirement to make this whole thing sensible in the first place, okay.
So I have a question concerning quantum computing. So we are trying to achieve it not only because it's a faster way to compute something, but also because it's more efficient. You know, we are very low in terms of efficiency. You know, Landauer principle.
You mean energy efficiency?
Energy efficiency. Yes, we are producing a lot of energy, and people believe that nature is more quantum than we are, and this is why, for example, brain is working. So I have a following question concerning the second flagship you were talking about. Do you believe the brain is quantum?
Yes, it is quantum.
Perhaps I'll offer some comments rather than questions regarding almost each of those things. First of all, you sort of discarded D-wave, and it turns out that D-wave is pretty efficient at what it's supposed to be doing, and namely sort of probing, sampling very large configuration space. And
with no guarantee of proper
actually,
results.
There is a guarantee because it samples something like hundreds of thousands or millions of states at once. And the whole point, and one has to understand that the objective of calculation is not to find the absolute minimum, but find a good minimum in extremely complex configuration space. And for that purpose, the computer proved itself. And if anyone is interested, I have dozens and dozens of papers. There have been studies done in various DOE labs and tests. And in terms of optimization, it's a pretty good optimizer. Of course, there are very vocal critics. For example, Matthias Treuer and Arthur Eckert are not greatly fond of D-Wave, but there are other reasons for that. The reason is that they are a little bit afraid that D-Wave might oversell the concept of quantum computer and will overshadow gate computer. And the next remark is that in March this year, there will be a conference run by ICM, University of Warsaw, on supercomputing frontiers, and we'll have a pleasure of hosting Professor Figueroa from Stony Brook, who has developed the largest computing communication network with quantum memories and Bell state sort of repeaters. So if anybody is interested in the realization of quantum communication network at this sort of state of the art, I welcome you at this event. Plus, on Thursday, 26th of February, there will be whole day quantum computing, sort of quantum programming of quantum computer workshop. Thank you.
Okay, so just to answer the first remark, I just wanted to say that D-Wave is doing some interesting thing, and they realize that they cannot solve some rigorously stated problems because their system is too noisy. So they moved to a more vaguely formulated problems, like optimizing transport, giving some, I don't know, study of medical data in order to infer something, and they run it to obtain some results, and maybe some of these results are interesting. I don't object to it, but they are just, I would say, walking in the dark, in my opinion, and trying to sample some problems that they devise can yield some results which they can interpret as interesting and maybe difficult to calculate classically, but a priori they have no proofs that classically it should be difficult to do it as well, and there were many instances that after they did it, some people developed analogous classical algorithms that did the same, but this is not to say that they should not develop their device. I agree that it's an interesting device and a lot can be learned from this. I just say that it's not following the proper path of reducing first noise of your components and then running the calculations. They do the opposite. They increase the number of components without taking care of their quality, and then they hope to get some results from it.
Yes, my question is as follows. You are talking about quantum technologies, but we know something which is really, which is in reality, it's a Japanese project of quantum technologies. And they are working in such thing as quantum wires and quantum dots. You are nothing said about it.
As I told you, my goal was not to give you a complete picture of the field. I just wanted to focus on 3 representative stuff that I think really tells you where we are. And I'm not sure whether the thing you mentioned makes some conceptual turnaround of this state of the art. It's like a breakthrough which is comparable to these things. I don't know. I wouldn't say. Okay, so then maybe you are right. Maybe it's important from the point of view of miniaturization of classical computing devices. But that's, okay, you can call it also quantum technologies. This was not in my talk.
Perhaps I will also comment on the question whether a brain is a quantum computer. Again, I'm sorry.
No, the question was, it's a quantum. Is it quantum?
Yeah, this is, again, a little bit of advertisement. March this year, 23rd, 24th of March or 25th, we'll have James Demkowicz from UCLA in Warsaw talking about his breakthrough work on nanowires, quantum nanowires, which behave like a sort of proto-brain system with memory and with forgetting, and mixes those concepts together. And where connectivity is extremely important. So you will have some answers there.
I think we're running over time, so maybe we should thank Rafał again for a very exciting talk. And see you next time.